Welcome to the topic quantum mechanics and electron configurations. In this lecture, we're going to be taking a look at the electrons and the vast amount of organization that they are actually in when they are buzzing around the nucleus. So let's take a look. So in a previous lecture, I talked about the history of like the parts of the atom and atomic theory. And way back in Dalton, he thought that everything was made up of little tiny things that he called atoms. He thought atoms were probably like little, maybe it's like marbles almost, little spherical things that make up everything. And then throughout the years, we've gotten a more clear picture after, doing experiments and making observations about matter and whatnot. And coming all the way to, kind of the modern era, which actually not too much in terms of parts of the atom has changed since like the basic parts of the atoms, since about like the 1930s. And from there, we just kind of gotten more detail into the different parts of the atom and what make up the different parts. So one of the major models is the Bohr model, and in this quantum mechanical model, the Bohr orbits. Remember, Bohr talked about how he thought electrons were revolving around the nucleus, kind of like planets revolve around the sun, in very fixed energy levels that are kind of 2D. Well, in this current model, which we call the quantum mechanical model, we still have certain energy levels in which the electrons are in. But we're calling them, something other than orbits. Okay, so this quantum mechanical model is basically kind of a representation of a probability map where electrons are most likely to be found. So if you think about, the solar system and how planets revolve kind of in 2D around the sun, then what electrons in atoms do is they're kind of buzzing around in like 3D, so like anywhere around the nucleus. Okay, so if we take a probability map, if we take a picture of an electrons kind of every second for hundreds minutes or whatnot and overlay them, we can get what are called probability maps to see where those electrons are more densely or more realistically able to be found. All right, so like photons, and photons is light, electrons exhibit a wave-particle duality, meaning that they act both as particles and as waves, which kind of makes it impossible to actually trace their actual path. So doing a probability map is much more efficient. So below on these screens, we have some different examples of the probability maps. So here we can see in this one that, if we're taking a look at the nucleus right there in the middle, right, then, most of the electrons are kind of really just in this circle area just outside of it. And in the second one, okay, it is more, actually that's a spherical one too, but this third one here, we can see it's kind of like a flower almost. All right, and so we're going to take a look and see at which energy levels or positions out from the nucleus do we get these different shapes of where the electrons are going to be. All right, so in the quantum mechanical model, there's different levels of organization for electrons. So we're going to talk about shells and subshells, okay, and orbitals. So those are kind of the three main, categories of organization of electrons. So the principal quantum number, which is represented by a big, number 1, 2, 3, 4, and so on, specifies the principal shell of the orbital. So if you remember back in regular chemistry, these were the energy shells that we talked about. When we were talking about, how many shells does argon have and how many electrons are in each shell, this is what we call the principal quantum number. So the higher the principal quantum number, the higher the energy of the electron. So Electrons that are in the first principal quantum number, or the first energy shell, have very low energy, and compared to electrons that might be in the fourth energy level, which are very excited, very high energy electrons. Okay, so within the principal shells, or these principal quantum numbers, we have what are called subshells. Okay, so subshells are denoted in letters. So the letters S, P, D, and F are different types of subshells that are within the principal shell. Okay, so the different, if we looked at probability maps of the different subshells, we can see definite patterns. So every S subshell is always spherical shaped. Okay, like this guy here basically just looks like a ball around the nucleus. All right, P subshells are what we call dumbbell shaped, like this one, where it kind of looks like, a dumbbell with not too much of a handle in between, but or like a figure 8. D subshells are flower shaped, so like this one here, look like a little simple flower. And then F subshells are kind of a bunch of flowers kind of all together, like a 3D flower almost, instead of a 2D flower. But those guys are super complicated, and we don't get to the F subshell. We don't worry about that too much. All right, so right now we know that we've got shells of energy in which electrons can be found, and within those energy shells we have different subshells that they can be organized in. All right, so reiterating what we saw on one of the first slides here, is this kind of probability map. So like I mentioned before, imagine taking a photograph of an electron and an atom every second for 10 to 15 minutes, and then you overlay all of them, and we end up with what we call a statistical representation of where these electrons are found. So if we see the shape like this here on the very left, where it's spherical, we know that we are looking at an S subshell, right, of electrons. This one too looks spherical, right? This one here, okay, looks like maybe a D subshell, because it looks like more of a flower shape. In fact, this could be a D subshell of maybe energy level 3, and then this bigger, right, flower here on the outside might be 4D or something like that, because it's further away from the nucleus. So looking at these, we can see the different shapes of subshells out from the nucleus. Okay, so what we're going to do is kind of go through shell by shell. We're only going to do the first 4 shells, because after that, number 5 shell, fish shell, those guys are pretty big atoms, and we can basically keep going with the same patterns that we're going to see in the first 4. All right, so we're going to take a look at each shell and talk about the electrons that are in the shell, how many subshells are in it, and how many electrons fit in each subshell, and so on and so forth. Okay, so the first shell, which we call principal quantum number 1, has 1 subshell. Okay, so the first shell has 1 subshell. We call that the 1s subshell. All right, and here we are going to talk about the last level of organization that I talked about at the beginning of this lecture, called orbitals. Okay, so remember I said that we have shells, subshells, and orbitals. Okay, this word right here, orbital. Orbitals are the third and final level of organization. And that's where kind of the electrons are actually sitting in. So S subshells always have 1 orbital that holds 2 electrons. Okay. So in the first shell, there's an 1s subshell, and each S subshell has 1 orbital that holds 2 electrons. So therefore, just like you found out in regular chem, we always said the first shell can hold 2 electrons, and this is how we can see that first shell holds 2 electrons, because it has 1 subshell, the 1s, and that S subshell has 1 orbital, and each orbital can only hold up to 2 electrons. Okay. Now, let's talk about shell 2. Okay, shell 2 is represented as principal quantum number 2, and the number of subshells is 2. Okay, in fact, I'm going to give you a huge hint. The shell, whatever shell number it is, that's how many subshells there are as well. Okay, at least for the first 4. So the first shell has 1 subshell, the second shell has 2 subshells. We're going to see in the next slide the third shell has 3 subshells, and the fourth shell has 4 subshells. Okay. But taking a look at shell 2, we have 2 subshells, and here we're going to have an S subshell and a P subshell. Okay. So we're going to have a spherical one and one that looks like a dumbbell. All right. Now, we already know that S subshells, right, have 1 orbital that hold 2 electrons each. Okay, but now we've got a P subshell as well. P subshells have 3 orbitals. Again, every orbital always holds 2 electrons each. So if we have a P subshell that has 3 orbitals and each orbital can hold 2 electrons, that means 6 electrons, right, fit in a P subshell. So 6 electrons are going to be in that P subshell of the second shell. And we also have a 2s subshell as well that holds 2 electrons. So if the S subshell holds 2 and the P subshell holds 6, we have a total number of electrons for that second shell as 8 electrons. Okay. So again, it lines up exactly with what we learned in regular chem, in high school chem, where we said the first shell holds 2 and the second shell holds 8. Okay. All right, so let's take a look at the third shell. So third shell is also called principal quantum number 3. And just like I said, going with the pattern that I mentioned before, if it's shell number 3, then it has 3 subshells. And in this case, we're going to have subshell S, subshell P, and subshell D. Okay. So we talked about S having 1 orbital, holding 2 electrons each. P shells having 3 orbitals holding 2 electrons each. Right? D subshells, okay, have 5 orbitals that hold 2 electrons each. So that means that every D subshell can hold up to 10 electrons, okay, because 5 times 2 is 10. So hopefully you see the pattern there too. It goes by odds 1, 3, 5 for the number of orbitals in each subshell. So S has 1, right? P has 3. D has 5 orbitals. Okay, so this third subshell, if we count them up, right, each S holds 2 electrons, each P subshell that has 3 orbitals holding 2 electrons each is 6, right, and then D subshells, we have 5 orbitals that hold 2 electrons each, so that's 10. So 2 plus 6 plus 10 is a total of 18 electrons that can fit in that third shell. All right, again, in congruence and alignment with what we learned in regular chem. 2, 8, 18 for that third shell. Okay. All right. Now in shell number 4, we didn't really talk too much about shell number 4 in regular chem. We just mainly focused on these smaller atoms. But let's take a look at shell number 4. So going along with the pattern that we had mentioned before, right? If we're talking about shell number 4, then that means he has 4 subshells. Okay, 4 subshells. We're going to see the S subshell, P subshell, D subshell that we've seen before, and now we're going to add the F subshell. Okay, remember that super, complicated 3D flower-looking subshell. Okay, going in alignment with the pattern of orbitals within each subshell. The S subshell has 1, P has 3, D has 5, so F must have 7. Okay, going along with that pattern of odds. So the F subshell has 7 orbitals that hold 2 electrons each for a total of 14 electrons in each F subshell. Okay, so if we take a look at the total for the 4th shell, if it has a S, P, D, and an F subshell, the S always holds 2, right? The P holds 6, the D holds 10, and the F holds 14. And when we add all of those together, we get 32 total electrons. Okay, 32 total electrons in that 4th shell. Okay. All right. So kind of real quick, like explanation or visual for the different types of organization that we have for electrons, right? The shells, subshells, and orbitals. Okay. So when I think of that, I kind of think of like an amusement park like Disneyland, right? So going into Disneyland, right? You maybe just think about like the castle in the middle. That's the nucleus, and around the castle is the different lands. We got like Tomorrowland, Frontierland, Fantasyland, Toontown. You know, all the different lands, right? So each land is like a shell, because they're surrounding that castle in the middle, and each shell, right, has different rides. So think of those as subshells. So the different rides within the lands are the subshells. And then when you hop on one of those rides, they have like different like numbers of like cars that you sit in, right? So like for example, if you go to like Alice in Wonderland, it's just one car, and 2 people can sit in that car. So like the different number of cars that go on the train type things in Disneyland are kind of like the orbitals. Okay, so like for example, like I said, Alice in Wonderland is just one car per group to go around. They're not like chained together or anything. But if you go on the Matterhorn, right, the Matterhorn has 2 cars that are chained together, and so that's like 2 orbitals, right, that are chained together. So think of the shells as being the lands, right? The subshells is the ride, and then the orbitals are the different carts that carry you around the ride. Okay, and just remember that each cart can only carry 2 people or 2 electrons, and that's kind of helps visualize, I think, this level of organization that we talk about in the atom. All right, so when electrons are kind of just chilling around the atom, and the atom is at what we call ground state, that means all of the electrons are in the lowest energy shells around the nucleus. Don't mind the motorcycle going by. We call that ground state. Now, if we excite the electrons in an atom, right? For example, if we put them in fire, like we did in regular chem, and like you'll do in this class as well, we excite them. We add energy to them, is what exciting means. So we add energy to the electrons in an atom. They go to what's called an excited state, and excited states are unstable. Pretty sure this motorcyclist is having fun going up and down my street trying to see if he can make any other car alarms go off. All right. Okay, hopefully we can get back to this lecture here. So, like I said, excited states are unstable. That means the electrons are not as close to the nucleus as they'd like to be. If you think about the nucleus as kind of like the home, and a lot of people feel safe at home, so the closer you are to home, safer, kind of grounded you are. As soon as you get far from home, especially if you don't know where you are, you're like anxious, like, I don't know what to do, just want to go home, right? So that's kind of like an excited state. So electrons usually fall back to their lower energy levels or their ground state, and when they do that, they release their energy in the form of light. So that's what we see. If you guys remember from regular chem, we did the flame tests where we put different substances in the flames and we saw different colors. It was cool. We saw like potassium made like a pinkish purple, and strontium was like a really bright red. Sodium was like a yellow orange. Lithium was that beautiful fuchsia color. That's because what we were basically visualizing was electrons going from a excited state outside of the nucleus, okay, far from the nucleus, back to their lower energy levels nearer the nucleus. And when that happens, they have to release the energy or release the stress and like craziness that, encompasses them when they're in an excited state. And they lose that energy and fall back down to their home ground state. Okay, so when they do that, they release energy, and we see that energy in the form of light. Okay, so you're probably either A, really confused, or B, asking, why do I have to know this, or what do I need to know about this? All right, so that all of that explanation kind of boils down to this skill right here, where we're doing electron configurations. Okay, so an electron configuration is an illustration, basically a sequence of letters and numbers that tell basically how or where those electrons in an atom are, like which shell, subshell, and how many are in each orbital for each atom. Okay, so basically it tells us where the electrons are around the atom and the order of which shells, subshells, and orbitals are filling up. All right, so when you take a look at an electron configuration, and those things look like this sequence down here. Okay, 1s2, 2s2, 2p6. So we can see that it is basically a sequence of big numbers. We call those coefficients. So the big numbers out front, the 1, 2, 2, 3, 3, 4, 3, 4. Okay, those are what we call coefficients, and that indicates the shell number. Okay, so if you look at your periodic table, right, you kind of have, let me just kind of draw a little outline here, right? Okay, so, you've got different rows, right? And then you've got different columns. Okay, this obviously is not drawn to scale, all right? But the shell number is actually the row number on your periodic table. Okay, so that first row going across from left to right, okay, here to here, this first row is shell number 1. So everybody in that row, hydrogen and helium, have their electrons in shell number 1, closest to the nucleus there. Okay, when we start with the lithium row, everybody in this row has electrons in the second shell. Okay, and then again, the third row is electrons in the third shell. So the coefficient is your shell number, which equates to the row number on the periodic table. Okay, so keep that in mind, because we're going to talk about how we get these different electron configurations for different elements. Okay, all right, then we also see the S, P, and D letters right here. Okay, and if we had a longer one, we'd see F's in there as well. All right, remember, those are the subshells. So the letter is the subshell. Okay, and we can actually equate them on the periodic table as well. Okay, the first 2 rows, those first 2 tall rows, are S subshell columns. Okay, so any element that has that sits on those first 2 columns has their last electrons in an S subshell. Okay, in the middle, okay, the transition metals in the middle, those guys are D subshell atoms. So their last electrons are found in a D subshell. Okay, and then we have the other 6 rows over here on the right hand side, and those are P subshells. Okay, so that's the P block, we call them. And then down on the bottom, we have the lanthanide actinides, right? That big row. And those ones are the F subshells. So those guys are the really, really big atoms. And we don't see that until we hit shell number 4. Okay. So those are the F and as in Frank subshells. Okay, so that's one way you can visualize on your periodic table, okay, the different parts of this electron configuration. Okay, the big coefficients we said are the shell numbers, which equate to the row numbers. The letters are the subshell, okay, which we call I call them the different blocks. Okay, blocks meaning like the different sections of the periodic table. Okay, and then last but not least, you guys see the superscripts. Those are the little tiny numbers up on top. Okay, kind of like exponents, or we call superscripts, and those tell how many electrons are in each of those subshells. Okay, so remember we said earlier that the S subshell has to hold 2 electrons, so that's why you see for most of the S's, you'll see that the number is 2. Okay, P's hold 6 and D's hold 10. All right, and that also equates to the periodic table as well. So you look at the S block, okay, on the left-hand side, how many columns do you see? 2, right? Because 2 electrons fit in that S subshell. Cool, huh? How many columns of transition metals are there? If you count them up in the middle, there are exactly 10 columns of transition metals. And guess what? Remember we learned that there's 10 electrons that fit in that D subshell. Okay. So kind of the periodic table gives you lots of information as long as you know what you're looking for. Okay. And then the final P block on the right-hand side has how many columns? 6. And how many electrons fit in that P subshell? 6. Okay, so it is kind of weird how it totally goes with the periodic table. And then F, if you look at the lanthanide and actinide, these guys have 14 columns because 14 electrons fit in the F subshell. It's really crazy. Okay, so we're going to keep this kind of organization in the periodic table in mind, all right, as we do some practice with writing out electron configurations. Okay. All right, so first though, let's take a look at a couple examples on this slide. So we have sulfur on the very left. All right, over here we have sulfur. Its electron configuration, all right, is 1s2, 2s2, 2p6, 3s2, 3p4. Okay, so sulfur kind of lives over here on the periodic table somewhere. Okay, in the 3rd row, right, in the P section, and or seat number 4 over. Okay, so sulfur is number 16 on your periodic table. So that means he has 16 protons, which means he also must have 16 electrons. And so when we take a look and draw out this electron configuration, what we're doing is we're placing all 16 electrons in shells and subshells around the nucleus. So for sulfur, the first 2 electrons are found in the first shell. The first shell has an S subshell, and there are 2 spots for them. So we say 1s with a little 2, right? So on our periodic table, that kind of fills up the first row here, all right? But we're not to sulfur yet, all right? We've placed 2 of its electrons, but it has 16 total. So we keep going on the periodic table, right? So we're going to fill up the second row now. So the second row has 2 in the first subshell, and then we keep going across the row, and it's 2p, and it fills up that p subshell, which is 6. So we see 2s2, 2p6. All right, so that gives us 6, 8, 10 electrons total. We're still not up to 16, and so we keep going to the third row. We fill up 3s2, and then we get to 3p, and we stop at 3p4. Because 3p4, we have 16 total electrons, and that is sulfur, right? If we added another one, you would have too many. So bottom line is to check yourself. If you add up all of your superscripts, it should equal the total amount of electrons for that element, okay? And we're going to see it always goes in the same pattern. We always start with 1s2, fill that row up, go to 2s2, fill that section up, go over to 2p6, fill that section up, right? And so on and so forth. So it's the same pattern every single time. It just depends on where you're stopping for each particular atom. So the other example here on this slide is krypton. Krypton here is number 36 on your periodic table. So that means he has 36 electrons that we need to figure out where they're going in each, shell and subshell. So just like sulfur, we start out with the first shell and subshell, 1s2, and then we go down to the second row and we fill up the S section with 2s2, and then we go over to the P section, 2p6, right? So that fills up to number 10, but that's not krypton, that's neon. So we keep going down to the third row, fill up the S section, 3s2, go over to the P section, 3p6, right? And then we go down to the fourth row, 4s2, and then you're going to see this trick right here. You're like, wait a second, we're in the fourth row, but why is it 3D? Okay. Interesting to note is that some subshells overlap each other. So what this means is that if the nucleus is here, right? Actually, let's put the nucleus right here, okay, under the krypton sign, right? And as we go further and further away from the nucleus, we're getting in higher energy shells. Okay, but what this 3D means is that the 4s is a subshell out here, and the 3D is actually closer to the nucleus than the 4s. Okay, in fact, let me put the 3D in a different color. So the 3D, okay, is closer to the nucleus than the 4s subshell, so it kind of overlaps. So that's why for the entire D section on the periodic table, right, it's typically in that fourth row, but we're going to be one shell less. So this first one is 3D, the second row, transition metals, is 4D. It's always one less than the shell that it's in. And then the same thing is for the F. These are two shells off. So remember, F started in shell number 4. So that means the first row has to be 4F, and the second row has to be 5F. Okay. So just remember those two, not variations, but two little kind of misnomers there on the periodic table that might trip you up. Okay. So when we're taking a look back at krypton, we're in that fourth row. We filled up 4s2. We have 3d10, and now we're going to jump back up to the fourth shell, 4p6, because krypton is all the way over here on that most right-hand column. Okay. And then again, if we added up every single one of these little superscripts, we added all those numbers together, we're going to equal 36 total electrons, which is exactly what krypton has, 36 electrons, to match his 36 protons. All right, so this slide here is a great example of what I was trying to scribble on the other slide, just showing how you can use your periodic table to take a look at the different sections, the S, P, D, and F subshells. If you kind of have trouble kind of remembering the order of them, you can think, left to right, San Diego Padre fans, okay? Or if you don't like the Padres, fail. I don't know, whatever, okay? SPDF, San Diego Padre fans, okay? And then on the other one to the right, we can see that we have the row number, right, for the shells, right, is the row number. And then this also clearly shows our D subshells, one less, right? One less than the row number, and our F subshells, two less than the row number or the shell number. Okay, so that kind of gives us a little bit clearer about the organization of the shells and subshells on the periodic table. Okay. All right, so we're going to take a look at a few examples and write out the electron configurations for a couple of different elements. Okay, so let's start with oxygen. Okay, oxygen is number 8. So that means he has 8 total electrons that we need to figure out in which shell and subshell these electrons are in. So remember, just like I showed you in the other examples, we always start with 1s2. We fill up this first row first, and there's there's an S subshell, and that S subshell holds 2. Okay, so that's going to get us over to here, but we're not quite to oxygen yet. So we're going to start filling the second subshell, right? Here, we're going to go 2 for the second row, S, and then we're going to fill this first subshell there with 2 electrons, and then we're going to go over to the next section, which is 2p, and we're going to see in here that he's 1, 2, 3, 4th, 1 over, so it's 2p, and we're going to put a 4 there to indicate that he's got 4 electrons in that 2p subshell. All right, so we're not going to have a full p subshell here because he's not neon, but it's 2 less than neon, so it's going to be 2p4. So oxygen is 1s2, 2s2, 2p4. Okay. Let's do another one, a little bit more complicated one. Let's do arsenic. Okay, arsenic is As, number 33, so he should have 33 electrons. In fact, let's go back to oxygen real quick and add up all of our subscripts. 4 plus 2 plus 2 is 8 total, and that's exactly what we see for oxygen, 8 electrons. Okay, so one way to check yourself. All right, so arsenic is number 33, and so we got 33 electrons to place in shells and subshells. We always start closest to the nucleus with 1s2. We fill up that row and we go down to 2s and fill this S section with 2, and then over to 2p, and then this time we're going to fill it all up, okay, with 6, and we're going to be going down now to the third row, 3s. Again, there's 2 electrons that fit in those 2 columns, and then we go over to the p, so 3p, and we will fill all the way up to 6, okay, because that's going to get us to argon, and we're not quite to arsenic yet. So we keep going, okay, go down to the 4th row, 4s2, okay, that gets us here, and then remember the D subshell is 1 shell lower, so we're going to say 3D, and we're going to fill the whole thing up with 10, 3D10, and then we're going to go 4P, and then arsenic is at seat 1, 2, 3. 4P3 is where we're going to stop. Again, it's not 4P6 because we don't fill all of the P subshell up. Okay, there's only 3 electrons that will fit in that subshell. All right, if we add up all of these numbers, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 3, 33 electrons. So we know we did it right because we ended up with 33 electrons, just like arsenic, who has 33 electrons. So that is kind of the pattern and sequence you do for every single element, row by row, section by section, seat by seat, okay, until they get up to where they're sitting on the periodic table. All right, the last kind of, I guess, concept, that's what I'm trying to say. The last concept in this lecture is what we call orbital diagrams. So after we get the electron configurations, going, and you're comfortable with those, so I would suggest, just grab a periodic table, point to an element, right? Close your eyes, point to an element, and draw out the electron configuration. Okay, and then you can Google it in order to see if you did it right. All right. After you've kind of mastered the electron configurations, there is another different way that you can represent how electrons are arranged around the nucleus. And these are what we call orbital diagrams. They show the electrons as arrows this time in boxes representing the orbitals. Okay, so it's kind of like we're zooming in on those orbitals and seeing how the electrons are arranged in the orbitals. So far we just know that each orbital holds 2 electrons. All right, but back in the late 1920s, early 30s, they figured out that these 2 electrons in each orbital are actually spinning with in opposite directions. Okay, so the electrons spin, all right, of these electrons are spinning in opposite directions. So think of them as a ball, one spinning in one way, the other spinning the other way. And this Pauli exclusion principle states that each orbital has to have no more than 2 electrons with opposite spins. So if one is spinning clockwise, the other one's spinning counterclockwise. Okay. So when we are figuring out, the electrons in different orbitals, we're going to represent them as arrows, and the direction of the arrows represents the different spins. So we'll have an up arrow and a down arrow in the same box to represent the 2 electrons that are spinning in different directions. Okay, and then there's one more rule that we need to know before we start doing these, and that's called the Hund's rule. Hund's figured out that when filling orbitals of equal energy, electrons fill them singly first with the same spin. Okay, so what that means is down here in the example that we have for 2p, you can see that instead of going, up arrow, down arrow in the first box and then an up arrow in the second box, Hund's rule states that you have to fill them singly first with all the same spin or all the same arrow direction. So we see up, up, up. All right, 3 different ones in different orbitals. Okay, before we start, I guess, like putting them together as pairs. Okay, so we got to keep that in mind when we are drawing out our orbital diagrams. Okay. All right, so over here on the right-hand side, let's take a look at these orbital diagrams and figure out what's wrong with them. Okay, so A, 1s looks good because we have an up arrow and a down arrow. 2s looks good, we have an up arrow and a down arrow. But 2p, okay, is not written correctly. There's 1, 2, 3, there's 4 electrons in 2p, right? But we have an up and down and an up and a down and a blank. Okay, so this is not following Hund's rule, where we should have basically an up, 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 and then we're going to pair 1 as a down for that 4th arrow. Okay. B, again, that's good, that's good, this is correct. Okay, so that's the correct one. C, taking a look at C, we can see a blatant misfiring here. We have in the 2s, we don't have 2 electrons in that orbital. We must always have 2 electrons in the orbital if it's at ground state. If it's excited, then we can, maybe argue that electron went from 2s to some outer energy shell because it's excited. But when we are doing electron configurations and orbital diagrams, we'll always be assuming that we are doing neutral atoms in a ground state, not excited. So we should have a down arrow in this one, which means we should have 1 less arrow in this one. All right, and then D, again, totally skipped the S. Can't do that. We have to fill them in order of those shells and subshells. So let's take a look at some examples. All right, this is the last slide in this lecture. Thank you for bearing with me. All right, And what we're going to do is we're going to be doing the electron configurations of some of these examples, and then also filling in the orbital diagrams. I'll do the first two with you, sulfur and gallium, and then you guys will have some time to do the other three on your own, and then you can check yourself just using Google. Just Google, electron configuration for aluminum, orbital diagram for aluminum, so on and so forth. Okay. All right, so in this slide, the superscript did not carry over from my PowerPoint. So you're going to see like this number here should be a superscript. This should be a superscript. Okay, so just kind of, if it's given for you, kind of follow along the pattern, 1S and then the superscript 2, and then 2S superscript 2. Okay, so we can see here for magnesium is number 12 on the periodic table. So he's got 12 electrons that we need to place in shells and subshells. So our configuration is, in fact, I will just write it again, 1s2, 2s2, 2p6, 3s2. Right? And if we add up, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12. All right, so we did our electron configuration correctly. And now for the orbital diagrams, the way this works is for each subshell, we have to put boxes to represent how many orbitals are in it. So remember, all of the S's will have one orbital, so that means we're going to draw one box for the S's. The P's have 3 orbitals, so we're going to draw 3 boxes for each P subshell. Right, and the D's have 5 orbitals, I should say. So anytime you see a D subshell, you're going to draw out 5 boxes. Okay, remember, in each box we're going to have 2 electrons, or up to 2 electrons. Okay, so for magnesium, we fill the first shell and subshell with 2 electrons, up arrow, down arrow, to show their opposite spins. Right, and then we start filling up the second row, first subshell, with 2 electrons, up arrow, down arrow, to show the opposite spins. Okay, for the 2p, this one is full, but remember the order of filling is always up, 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 separately first, and then we pair them up, down, down, down. Okay, so keep that in mind. And then again, 3s is also filled with an up and a down. Okay, so that's magnesium. Now let's take a look at sulfur. Sulfur is number 16. So we're going to see on your periodic table, if you look up sulfur, he is basically, 2 to the left of argon. All right. So let's take a look. We have 1s2, 2s2, 2p6, 3s2, 3p4. Okay. So when we add up 2 plus 2 plus 6 plus 2 plus 4, we get a total of 16, and that is sulfur's electron configuration. All right. So when, when we do our orbital diagrams, we're going to fill up each of these shells and subshells as we go. So 1s is going to be filled up with an up arrow, down arrow. Then we fill up the next energy level, 2s, up arrow, down arrow. Then we fill up our next energy level, 2p. This has multiple boxes, so we need to do up, 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 and then there's 6 of them, so each of them's gonna have a pair, down, down, down. Okay. 1 box for 3s, it's all filled up, so we get an up and a down. Okay. And then for for sulfur, we have 3p4, so there's going to be 4 electrons. So we do up, up, up. There's our 3, and then we're going to have 1 pair, or 1 electron there to pair the first one as a down. And so it's going to look like that. Okay. So we can see he's 2 electrons away from filling up this shell and subshell. Okay. So if he gained 2 electrons, he would fill up his shell and subshell. Which is exactly what sulfur does when he makes a bond. He goes out and seeks 2 more electrons to fill up his shell and subshell. All right. So this all goes, explains basically. This is an explanation for bonding, how electrons are either shared in order to fill up shells, or if they are given and taken, it explains how many are given and taken in order to end up with a full shell. All right. Last but not least, we have, or not super last. Last one I'm going to do with you is gallium. All right, gallium is number 31 on our periodic table. Okay, so he is in that 4th row. So we're going to do a little transition metal 3D action here. So we're going to have a pretty long electron configuration, and then we're going to have lots of boxes to fill in for our orbital diagrams. Okay, so I'm going to take up more room than what's on the screen, but you should have plenty of room on your paper. So let's take a look. We'll start as always with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1 for gallium. Okay, adding up all of our superscripts. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 1 is 31. Perfect. All right, so now for every single one of these shell and subshells, we need to draw boxes, right? So we're going to draw one box for the 1s subshell. We have 2s, which is s have one orbital, so we just draw one box. The p's have 3 orbitals, so we're going to do 3 boxes for 2p. All right, next up is 3s. S is just one box. Okay, then we'll have p again, so we have 3 boxes for that p subshell. Then we're going to have our 1 box for our 4s. And then D. Remember, D's have 5 orbitals. So we're going to have 5 boxes. Oops, not 4. This is our 3D. Okay. And then we have in the P's, P has 3 orbitals, so we have 3 boxes for our 4p. All right. So now we got to do is fill them up. So S's, up arrow, down arrow, up arrow, down arrow. Okay, everything's going to be filled up with 2 electrons until we get to our last section there, the 4p. All right, so for the 2p's, up, 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 down, down, down. 3s is an up, down. 3p's, up, 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 down, down, down. 4s, up, down. 3d, again, Hund's rule says you got to do each one separate with the same spin, and then we pair them up with opposite spins. And then back when we get down to 4p, remember we only have 1, so we'll just do an up arrow in the first box and be done with it. So if we count up how many arrows we have, we should have 31 arrows, representing gallium's 31 electrons. Okay, so that's how the orbital diagrams work. So if you have any other questions, try to Google the information, or look on YouTube for any other explanations about orbital diagrams. I'm sure other people have good videos on how to do them as well. All right, so this is part 1 of quantum mechanics. You'll find part 2, all right, on the website as well.